Let's talk about identical experiment did not give identical result in quantum mechanics.
In quantum mechanics, even if you set up an experiment in the same way each time, the outcomes can differ because of the probabilistic nature of quantum systems. Measuring a quantum state collapses it to one of the possible outcomes with probabilities dictated by the wave function. So you might get different results each time, even though your initial setup is identical. This is fundamentally different from classical physics, where identical conditions lead to identical outcomes.
How can we experimentally prove that thing?
One classic way is through a series of repeated measurements on identically prepared quantum systems. For example, take the double slit experiment with single electrons. If you send them one by one, each electron hits a random spot on a screen. But as you repeat the experiment many times, a clear interference pattern emerges, revealing the probability distribution. This experimental pattern, only visible statistically, proves that each identical setup leads to different individual results, but a predictable distribution.
So you are suggesting interference pattern emerges. Then if that experiment give identical result, then what would be the result?
If quantum systems gave identical results every time, you'd lose that probabilistic nature. In something like the double slit experiment, you'd see electrons or photons consistently hit the same spot, or form a pattern resembling two distinct lines, like classical particles. There would be no interference pattern. Every shot would go to a predetermined location based on the initial conditions, just like in classical mechanics.
So you are suggesting instead that they are giving that interference pattern, meaning that every time it hits a new spot.
Exactly. Each individual quantum particle lands at a seemingly random spot, but over many identical runs, those random hits build up into a predictable pattern, like the interference fringes. Each new spot is random, but the overall pattern follows the probabilities defined by the quantum wave function.
So you are suggesting that given the system, if the particle interact with the double slit experiment and then the interference pattern shows that it's a probabilistic distribution, and then that is the weirdness of quantum. Instead, in the classical, we had got the spot or something like that, but instead we get a interference pattern.
You've got it. In classical physics, we'd expect particles to go through one slit or the other, landing in distinct predictable areas, just spots. But quantum mechanics gives us that interference pattern, reflecting the underlying probability distribution. The weirdness is that even a single particle, when not measured at the slits, behaves as if it interferes with all possibilities, producing a pattern that only emerges when you look at many, many outcomes.
Okay, but how did this confirm for the first time that identical experiment did not give identical results, and those thought theoretically frame the quantum physics and how, when they observed it?
The idea really took hold with early quantum pioneers. Max Born first suggested that the wave function's squared magnitude gives probabilities, but the famous confirmation came from experiments like those of Davison and Germer in the 1920s, who observed electron diffraction, something only explainable if electrons behave like waves. Later, when single particle double slit experiments were done, especially in the latter half of the 20th century, scientists saw that even one particle at a time created step by step an interference pattern. This confirmed that identical conditions yield probabilistic, not deterministic results, a key pillar of quantum theory.
It yield probabilistic, not deterministic result. Okay, so but how that pattern is classically different that we observe? Suppose interference and diffraction. I need a strong intuition to understand.
In classical physics, if you fired little balls through two slits, you'd just get two piles behind them. Each particle follows a definite path. But in quantum mechanics, particles behave like waves. Waves from each slit spread out and overlap, creating regions where they reinforce, bright fringes, and where they cancel, dark fringes. So instead of two piles, you get an intricate pattern of alternating bright and dark bands. It's like the particle explored every path at once, classically unimaginable, but fully real in quantum experiments.
I thought the main problem is while I was thinking, so wave enter the double slit experiment and we get the wave like probability distribution. So there is no particle, so we are not interacting particle with the double slit, na?
It's understandable to feel that way. The tricky part is that quantum objects, like electrons, are both particles and waves. When we don't measure which slit they pass through, they act like waves, creating that interference pattern. But when we measure which slit they take, the wave collapses, and we see particle like behavior with no interference. So, yes, we do send particles, but their wave like nature is what produces that pattern.
How can you say that we send particle? Because beam of electron pass through double slit. One example, I remember that part.
We say particle because when we detect them, they show up as individual localized impacts, like tiny dots on a screen. Each electron arrives as a discrete event. But before detection, the electron's behavior is governed by a wave function, which spreads out and interferes. In other words, they're quantum objects, neither just a particle nor just a wave, but something that acts like both, depending on what we look for. The double slit experiment reveals that duality in a beautifully puzzling way.
But we are not passing particle through that slit now. We are passing wave function through that slit.
It's a subtle but important point. In quantum mechanics, the wave function is a mathematical tool that describes the particle's behavior, its probabilities. But the physical electron or photon still goes through the slits. When we detect it, we detect a particle like event. The wave function tells us where it's likely to be. So we send a quantum entity that has both wave and particle characteristics. The pattern we see emerges from its wave like behavior, but when it's detected, it's always a particle hit.
So interference and diffraction patterns are wave functions.
Yes, exactly. The interference and diffraction patterns are the result of the wave function's behavior. The wave function describes how the probability of detecting the particle spreads out and interferes, creating those bright and dark regions. But when you actually detect something on the screen, you don't measure the wave function directly, you measure a particle's impact. The pattern is the grand wave-based probability distribution of where those particles are likely to hit.
So what we have discussed till now.
We've explored how in quantum mechanics, even if you set up the same experiment identically each time, you get different results. We used the double slit experiment as an example. Individual particles, like electrons, produce an interference pattern over time. This pattern arises from their wave function, which behaves like a wave. Yet when we detect them, they appear as particles. So we confirmed that quantum systems are inherently probabilistic. The interference pattern is wave-like, but each detection event is particle-like, revealing that dual nature.
Can you give a more detailed explanation what the statement you are referring that like wave like or particle like thing?
Sure, when we say wave-like, we mean that quantum entities, like electrons, are described by a wave function. This wave can interfere with itself, producing patterns of probability. So when many particles are sent through slits, we get interference patterns, just like waves do. But when we say particle-like, We mean that when we measure or detect them, we always get a single localized hit, like a classical particle. So the electron travels in a wave, interference, but when you detect it, you get one spot, like a particle. This duality is at the heart of quantum mechanics.
So that spot, like a particle, is just also a probability distribution that we got on the screen. So why you are referring that we are getting a spot, but we are getting a in the screen that we detected something like that?
Great observation. Each individual spot is indeed a single detection event, the particle arriving. But the key is that if you repeat the experiment many times, those individual spots build up a pattern. That overall pattern, bright and dark regions, represents the probability distribution given by the wave function. So the pattern emerges from the accumulation of many particle detections, each one probabilistic.
How can you tell that these particles like behavior or like wave inter and particle spotted, and why only two slits works here?
We say particle-like because when we detect, we see a localized impact, like a particle hitting a screen at a single point. But the way those points arrange into an interference pattern tells us the particle behaved like a wave before detection. Why two slits? With one slit, you'd only get a broad pattern, no interference. Two slits allow the wave function paths to overlap and interfere, producing the characteristic fringes. It's this interference that shows the underlying wave behavior, even though we detect particles. It's that duality, wave evolution, particle detection.
So you are telling that localized impact, particle hitting on a screen, and the interference pattern, Y2 slit, with one slit you would get the broad pattern, no interference. So to satisfy the interference, we have to take two slits and wave function part to overlap and interfere, producing the characteristic fringes. It's this interference that shows the underlying wave behavior, even though we detect particles, that duality. So what about four slit?
With four slits, you get an even more intricate interference pattern. Each pair of slits contributes its own wave-like interference, and when you have more slits, these patterns overlap and combine. The result is a more complex, finely spaced pattern of bright and dark regions. In other words, the more slits, the richer the interference pattern. But the principle stays the same. Wave behavior governs the probabilities, and particle detection gives you the discrete spots.
Why this idea was very important and a key role that it plays.
This idea was revolutionary because it shattered the classical worldview. Before quantum mechanics, people thought particles always had definite positions and paths. But these experiments showed that on the quantum scale, reality is probabilistic. The duality, wave behavior before detection, particle behavior at detection, forced a new understanding of nature. It forms the backbone of quantum mechanics, shaping everything from atomic theory to modern technologies, like transistors and quantum computing.
How this theory work on transistor and quantum computing? Can you give a small intuition?
In transistors, quantum principles explain how electrons move through semiconductors. Quantum tunneling, for instance, allows electrons to pass through barriers they classically couldn't. In quantum computing, we harness quantum superposition and entanglement. Qubits can be in multiple states at once, like waves, until measured. This allows quantum computers to process information in parallel, solving certain problems dramatically faster than classical computers. In both, quantum behavior gives us control and capabilities we can't get from classical physics.
How this is related with YDSC, because it shows that wave-like behavior and the
The double slit experiment was one of the first clear demonstrations of wave particle duality. It showed that quantum objects, like electrons or photons, act like waves when they travel, creating interference patterns, but appear like particles when detected. This concept of duality underpins quantum mechanics. The same duality governs electrons in transistors or qubits in quantum computers. So the YDSE was a historical and conceptual cornerstone, proving that quantum systems don't behave purely like classical particles or waves.
Okay, thank you.